For a long time, electric current and magnetic field were thought to be two completely unrelated things. In 1820, a scientist by the name of Oersted noticed that a current in a wire was affecting a compass needle. The only way that could have occurred was if the current within the wire was producing a magnetic field that was moving the needle of the compass. Say we have a wire where the current is moving in the up direction. What we find is that the magnetic field forms in concentric circles around the wire. We can use another form of the right-hand rule to determine the direction of the magnetic field. Point your thumb in the direction of the current and wrap your fingers around the wire. The motion of your fingers will point in the direction of the magnetic field. Experiment has shown that the magnetic field produced by a long, straight, current-carrying wire is the current times the permittivity of free space divided by 2 pi times the shortest distance to the wire. Now each segment of the current within the wire of any shape produces a magnetic field just as if it were a long straight wire. The total field then is the vector sum of the fields in each segment. As you might imagine, wires can be formed in an infinite number of shapes, and the math involved with solving something like this is both beautiful and terrifying. For this class we will only cover the general idea. But say we have a circular wire. Using the right-hand rule, we can determine the magnetic field as it is shown on the right. What you will notice here is that the magnetic field is not uniform. The fields are different in the magnitude and direction at different locations. An application of this idea is a solenoid. A solenoid is a long coil of wire with many loops. This shape causes the magnetic field inside to not only be fairly uniform, but also very strong, while on the outside it is very low.